Are we in the Matrix? Every year, new indirect evidence points to us living in a simulated system. At this rate, in about 30 years, the virtual universe theory might become as mainstream in the scientific community as the theory of evolution is today. The world's first programmable computer, the Z1 by Konrad Zuse, could perform 2 floating-point operations per second, while modern computers are 27 times faster. This breakthrough was achieved in just 79 years. Scientists predict that in the next 100 years, computing power will increase by millions of times. It's hard to imagine what kind of world our descendants will live in. Today, virtual worlds like Grand Theft Auto are astonishing due to their detail. It's easy to imagine that in the next 50 to 100 years, they will be indistinguishable from reality. Distinguish. In fact, we might even create virtual universes where characters truly have the ability to think, possessing minds similar to ours, yet unaware that they live in a simulated environment. This is terrifying on many levels. What if we are already such characters? What if the entire world you see outside your window is simulated? Philosopher Nick Bostrom introduced the hypothesis that our world might be virtual to the public as early as 2003. The core idea is that if there are many technologically advanced civilizations in the universe, then they very likely find some kind of answer. And now we are going to do just that. Evidence that we might be living in a virtual world. Grand Theft Auto 5, or GTA 5 for short, is a great example of how this can all be realized. In the game, on the many streets of the virtual city Los Santos, you'll see a very familiar scene. You're surrounded by speeding cars, and the sidewalks are crowded with people. Overall, everything is very similar to real life. In the game, no matter where you are in Los Santos, this scene always accompanies you. There is the capability to create a simulated world similar to the one where you or your child sits in front of a computer, only it's millions of times larger and more realistic. This means that right now, you or I might be playing the role of an NPC, a non-player character, in some alien sandbox game. People are indeed taking this idea seriously. For example, Elon Musk stated in 2016 that the probability of our reality not being simulated is only 1 in a billion. When you hear such statements from someone like Musk, you start to seriously doubt the nature of our reality. This forces us to at least begin to seriously search. If you turn a corner, you'll see more cars and more pedestrians. Therefore, when you're standing on the streets of Los Santos, you might think that real life is happening in every corner of the city. But in fact, that's not true at all. You can't forget that everything you see is just an illusion built for you. When you're at a place called Street A, Street B is absolutely empty, with nothing happening there. The game is actually dynamically rendering the lively street in front of you, while other streets are immersed in silence. Detailed, while the textures and objects behind the player and out of sight are simplified as much as possible, or even disappear completely unless potentially needed. This allows the computer to reduce the load on the gaming platform while maintaining beautiful graphics. In GTA 5, if you look down from a high place at a certain location, the whole city seems to be in the palm of your hand, and you can see cars speeding back and forth on the many streets. Does this mean that the console or computer's computing power is enough to render such complex and detailed graphics? Let's not jump to conclusions. The matter almost non-existent. All modern video games follow this principle. When you're not in a specific location in the virtual city, there's absolutely nothing there. No pedestrians, no cars, not even the city itself. Developers have optimized the game to reduce the burden on computer hardware. That's why you can enjoy such incredibly realistic graphics and game physics. These are the modern masterpieces of the gaming industry. If a player or character turns to look at something, the computer will render the image in front of them as much as possible. For objects far from the observer, like cars, the physics rules in the game are also simplified. If we launch a rocket into the distance, we can barely see it explode. If we fly closer, the explosion looks more detailed and realistic, which requires more computing power. The next example is Civilization 5. If you quickly move the camera from one end of the map to the other, you'll see locations loading before your eyes. The game engine isn't perfect, so we can see how the view responds to our actions, making us aware of our presence. Observing it, the very presence of the observer will affect the game world. Any future electronic games will also operate in this way. Even if super powerful computers can simultaneously calculate all large objects within a wide range, small details will still need rendering over the years. Flies, blades of grass, and even numerous microorganisms, all these will only load under the observer's gaze. It's all about optimization. After this game-related setup, we now turn to the theory that we live in a simulated world similar to the Matrix. Evidence. You might know or remember one of the most famous experiments in the history of physics, Thomas Young's double-slit experiment. This was a true breakthrough in physics, leading many scientists into the field of quantum mechanics. If you throw a solid ball at a barrier with a slit, the screen behind the barrier will show a single spread out stripe indicating the impact point. If the barrier has two slits, then two stripes will appear. But what happens if a wave is directed at the barrier? The wave will pass through the slits and spread out, with its area of greatest impact being a single slit alignment similar to the case of a solid ball. However, when a second slit is added, everything changes and a series of alternating interference fringes appear on the projection screen. When we shine light onto the double slits, this is exactly what happens. This is how Mr. Young demonstrated the wave theory of light. If light were particles like solid balls instead of waves, it should behave like solid balls, and only two bands of light corresponding to the two slits would appear on the screen. But this did not happen. Later, it was discovered that electrons and protons behave in exactly the same way, indicating that they also seem to exist in waveform rather than as points. There was a hypothesis that perhaps light and other particles might collide and scatter. To verify this, physicists decided to fire electrons one at a time at the target. Can you guess what happened? Incredibly, an interference pattern still appeared on the screen, as if a single electron somehow split into two waves passing through both slits simultaneously and then interfered with itself. This is clearly impossible, so physicists tried to determine which slit the electron actually passed through. We installed measuring instruments for monitoring. Another seemingly impossible phenomenon occurred. Electrons no longer behaved like waves, but like particles, leaving two clear, non-interfering stripes on the screen. Scientists had to acknowledge a shocking fact. Our observation or measurement behavior collapses the wave function of photons, making them appear as point-like particles. Under the influence of observation, electrons behave like particles passing through only one slit, rather than both simultaneously. Doesn't this explanation sound a lot like how a game engine operates? This might lead you to think that our world is like a game running on a computer, where the computer's processing power isn't enough to calculate the movement of every particle, so it uses a simplified model, only performing precise calculations when an observer needs to check. It calculates particles accurately only when observed, to maintain the illusion of reality for the observer. In 1803, when Thomas Young published his experimental results, humans couldn't imagine virtual reality, but this might be one of the earliest experiments revealing the existence of our simulated universe. In 1927, Bohr and Heisenberg proposed the famous Copenhagen interpretation, suggesting that particles are both waves and particles. When the wave function of an electron interacts with the screen of a measuring device, once measured, the wave function collapses and the electron only behaves as a particle. This means that it is not the observer themselves that affects the observation results, but the measuring device. But even if this theory is correct, it does not negate the hypothesis of a simulated matrix world. For example, a programmed photon might propagate as a wave in a network, and when a node is overloaded, it would reboot and transform into a particle form. This method can explain both quantum waves and the collapse of the wave function. The second mainstream interpretation of particle behavior is the many worlds interpretation. Simply put, its core idea is as follows. We can assume the existence of parallel universes where the same natural laws operate. For every measurement of a quantum object, the world splits into multiple versions. Each universe sees its own measurement result and evolves accordingly in its own universe. To a layperson, this explanation seems quite bizarre. But the world is free, or at least we think so. Therefore, anyone can choose the explanation you most agree with. 20 years ago, at a seminar hosted by the University of Maryland, a survey was conducted among physicists. 13 supported the Copenhagen interpretation, 8 supported the many worlds theory, and several other scientists chose less popular options, while 18 participants opposed all known explanations. The debate continues to this day. In 2006, scientists conducted a more complex double-slit experiment, this time incorporating a delayed choice element. In short, particles were once again emitted through a barrier with two slits, but this time the observation of which slit the particle passed through was made after the particle had already passed through the slit, but before it hit the screen. It's like the observer only opened their eyes at a specific moment. Surprisingly, at this point, the electrons behaved like particles, as if nothing had happened from the moment they were fired from the electron gun, as if they hadn't passed through both slits simultaneously, and didn't exhibit wave properties. It seems as if the electrons knew in advance they would be measured. The second hint of the existence of a matrix world comes from the universe's maximum speed, the speed of light. The theory suggests that nothing in a vacuum can move faster than a photon. The speed of light is both a limit and a constant. Moreover, the faster an object moves, the slower time passes for it. When the speed reaches 300,000 kilometers per second, time completely stops. This means that if you were on a spaceship traveling at this speed, you could reach a distant galaxy 3 billion light years away in the blink of an eye in your own time. However, for an observer on Earth, the same journey would take years to complete. Therefore, for a photon, time stands still at 0, and it cannot accelerate further because to do so would require time to pass even slower, and time has already stopped. which is clearly impossible. But why is there such a relationship between speed and time? Why are space and time interconnected? The answer points to the virtual world hypothesis. The matrix hypothesis suggests that the speed of light is a product of information processing, meaning that the world is updating at a certain rate. Although this is faster than any supercomputer we currently have, machines need to be infinitely faster, but the principle is the same. Time slows down as speed increases. Because virtual reality relies on virtual time, each processing cycle is a time unit. When the computer runs slower, playback time also slows down a bit. This is very similar to how time in our world slows down as speed increases or when approaching a massive object. This suggests that our universe might be virtual. It's possible to assume that in a spaceship traveling at extremely high speeds, the system's processing cycle would pause to save resources. The third piece of evidence, and the most compelling proof that we live in a matrix simulation, is quantum entanglement. So what exactly is it? A photon traveling through space can be thought of as spinning, meaning it has a property called spin. In fact, photons aren't really spinning, but this is a simplified model. Therefore, physicists believe that the most likely scenario is that a particle doesn't even have a specific spin state before it is observed. In other words, if no one is looking at the photon, it can't determine which direction to spin, so it's considered to be in some kind of superposition. It seems that nature finds it difficult to calculate the spin of every particle, so it uses a simplified solution for this. But similarly, when an observer appears, the particle becomes more physically complex and real, and its spin state is calculated. Albert Einstein proposed an experiment to test a certain interpretation, and some very interesting results were obtained from this experiment. The essence is this. For example, when an atom emits two photons in different directions, due to the law of conservation of momentum, their states will be correlated. If the spin direction of one photon is from bottom to top, then the other will be from top to bottom, and their spin directions are always opposite. This is what's known as quantum entanglement. But remember, the photon doesn't know which direction to spin before being observed. Therefore, in this situation, if the act of observation causes one photon to choose a state, its entangled partner must immediately have the opposite spin direction. In other words, just by observing one photon, we influence the other photon. Spin. Even if we don't observe the second photon, and the second photon not only needs to choose a spin direction, but must do so immediately. Even if these two photons are far apart, this means that if the entangled photons are somehow sent to opposite ends of the universe, the information about how it should spin must travel at several times the speed of light across the universe to reach its partner, so it can immediately acquire a spin state. This is simply unbelievable because it violates the known laws of physics. In a vacuum, nothing can move faster than a photon. However, the second photon can still obtain this information in zero time. But the question is, how does the partner in this pair of entangled photons know at such speed that its companion has been observed and thus chooses to spin in a specific direction? Einstein firmly believed that such instantaneous connection was impossible. He hypothesized that when entangled particles are produced from an atom, they already contain information about the past, and know which direction they would spin if observed. In other words, the observer does not change things, but merely identifies the spin state of the particles. But 17 years after Einstein's death, it was proven that this unparalleled genius was wrong on this issue. Yes, Einstein was wrong. To prove whether particles have preset information about spin direction after being observed, physicist John Bell designed a complex and ingenious experiment, and the results were astonishing. Bell proved that entangled particles have no idea which direction they will spin before being observed. The spin of the photon is randomly determined after measurement. This result proves that basic entangled particles can transmit information at speeds far exceeding the speed of light. This experiment brings us more questions than answers. In 2008, a group of researchers at the University of Geneva decided to determine the speed of information exchange between entangled particles. They separated two entangled photons to a distance of 18 kilometers, measured one of the particles, and recorded the reaction speed of the other particle. The technology they used could measure delay times up to 100,000 times the speed of light, but the results showed that even such a tiny delay did not exist. It is proven that the speed of information transfer between photons is at least 100,000 times the speed of light, and it might even be instantaneous. Perhaps Einstein was right in saying that instantaneous communication is impossible in the physical world, but if we replace the physical world with virtual reality, this instant connection is easily explained. When two photons are entangled, their programs are merged into a single joint node. No matter where they are at the moment, this program combination will cause both pixels to respond simultaneously. When one particle is measured, its program randomly selects a spin state, and the second particle's program reacts immediately. This explains why distance doesn't matter, as the process doesn't need to travel to another pixel to instruct its spin. Even if the so-called screen is as large as the universe, physicists often say that no one truly understands quantum mechanics, but if we assume our world is virtual, everything becomes clear quickly. Scientists use quantum mechanics to describe fundamental particles and their interactions, and general relativity to describe the macroscopic world. If these two worlds coexist in nature, there must be a theory that reconciles both. The simulation hypothesis was born for this purpose. It meticulously explains the mysteries of the Big Bang, space curvature, tunneling effect, dark energy, and dark matter, all of which can be interpreted under the assumption of a virtual universe. Some say that even if the simulation theory is proven, it won't change anything, but official confirmation could greatly boost new research, and perhaps scientists could discover loopholes in the program of our world, and use them to create new technologies. For example, if quantum effects stem from the virtual nature of the universe, then the birth of quantum computers or quantum cryptography could be seen as exploiting the rules of the world. Are we in the Matrix? Every year, new indirect evidence points to us living in a simulated system. At this rate, in about 30 years, the virtual universe theory might become as mainstream in the scientific community as the theory of evolution is today. Perhaps soon schools will teach us that humans live in a virtual world, although realizing that we might just be a complex program with emotions and self-awareness can be somewhat disheartening. But Elon Musk believes this is a good thing. Breath. The simulation hypothesis answers the Fermi paradox. Why is the universe so silent? It also suggests that intelligent civilizations have the ability to avoid self-destruction and can even create virtual worlds through technological advancement. For Musk, life in the Matrix is considered an ideal utopia. By the way, he genuinely hopes this is true. Additionally, I recommend watching the movie The 13th Floor and The Matrix Trilogy. Don't forget to like and subscribe to the channel, or Agent Smith might soon come knocking at your door.